See that? Pages. Smooth. You guys are so unimpressed. So at 2, I know that my denominator was a 5. 2 squared is 4. 2 times 2 is 8. 8 plus 2 is 2. Isn't that where my asymptote is? This might be the jump one. All right, let's try it again at. Okay, let's try the next one at 3, just for fun. What's 3 squared? What's up?
Shouldn't you put the dot around thought? Shouldn't it be over 1 1?
I'm old. Can't count. You guys know that by handing out papers. It should be the least of your worries. I use 3. 3 squared, 9. 9 and 1 is 10. 9 times 2 is 18. 18 and 3 is 21. So it's over 2. Now, is this the one that has the jump discontinuity? I think it is. I don't be worried. We don't really teach you guys this one yet. Let me show you this. Alpha y equals 2x squared. Oh, I know why. This has got the imaginary root. That's why it does this. Oops. I think I need to change my window. All it's doing is that this graph is one of those weird ones. In that there is that asymptote that goes here. But the asymptote itself is really only for a portion of the graph. Yes, it does jump the asymptote on the right-hand side. We just saw that because we used 2, we got 2. Do you guys see that? One of the reasons that that happens is because of the imaginary root. Okay? You guys get into more of that discontinuity portion of this next year. We don't go into depth into reasons as to why things like that occur. We show you that more in pre-calc. For right now, we're getting to the idea of, can we just plug and chug numbers to get a general sense of what the graph is doing, along with the asymptote's placements, okay? Does that make sense? There's also going to be something here in a little bit. I don't remember if there's, I think it's an example I show you guys today, where you have factors in the numerator and denominator that cancel out. They simplify out, but yet they simplify out at an asymptote, and it goes through it. There's a reason that happens because of the hole that was created by the simplification. It's kind of weird how it looks. I forget what number it was. But that's kind of how this one works through. Let me see here. Yeah. And then I'll show you guys the other one here. Which one did that? I don't think any of the ones you guys had last night did that jump continuity. It's just the stuff I'll show you today. X-intercepts, real zeros of the numerator. X cubed minus 27 is 0, so x is going to equal 3. Do I need to factor that out like you would at the difference of cubes? No, because I'm just finding the real answer. Because if you remember, if you factor out difference of cubes there, you wind up with one real solution, the other two are always imaginary. Remember that? So you don't have to do that. Set it equal to 0 and go. All right. So that gives your x-intercept. Your vertical asymptote is going to be at x equals 0. Just set it 2x equals 0. Horizontal asymptote, you have m is greater than n. So that one was the no horizontal, but this one will have a slant one. And I'll show you how we get to that slant one here in a minute. Okay. So if I go to graph this one, Actually, let's do this. Let's have more space. If we go to graph this one, we know we have an x-intercept at 3. Vertical asymptote at 0. And that's all you know right now, okay? So what I would do is trying to figure out what this graph is going to do. I would just start to pick a couple of numbers. I would probably do my -2, -1, 0, 1, and 2. Just because it's on both sides of that asymptote. I do have that one value of 3, and those other points just might get me somewhere, okay? So, and they're not terrible to work with. If I take -2 and cube it, I get -8. -8 minus 27 is -35. Divide that by -8, you get a positive 4 something? 4 and change? Bless you. Bless you. We got that. Sir?
Where'd you get the 8? The -8?
-2 cubed. I'm plug and chug.
On the bottom, on the denominator.
Oh, it should be 4. Sorry. I did 2 times, yeah, so this should be -4, so this should be at -8. Thank you. Right up here. Okay. -1. -1 cubed is -1. -1 minus 27 is -28. Divide that by -2, and I'm going to get 14. Okay with that? So it's going up this way now.
What, how do you know which numbers to use?
I'm just guessing. I saw that I have an asymptote, so I'm trying to see what's happening around the asymptote. That's all. Just like we did yesterday when you had that. Remember on Tuesday when I said plot the points on either side of the asymptote? It'll give you kind of a direction of where things are going. It's kind of the same process.
Anytime n is greater than n versus n.
Yeah, there will be. But this one's a little bit weirder. So as you go into the next part here, we have at 0. 0, again, we don't want to use 0 because it technically is our asymptote. So this will be the undefined value. That won't work. But if I go to 1, I get 1 cubed, which is 1. Subtract 27, I get -26. And I divide that by 2, and I get -13. So I'm back down here now. My best guess is that at 2, it's going to be getting up this way. And I got to figure out what's happening to the right of that. Everybody see where I'm going with this? Now, the other concern is what's happening here. This is going this way, but I need to figure out where is it going here. Is it curving back and around, or is it just going downward? So maybe another best idea would be just to pick a different number away from everything. See where I'm going here? I'm just plugging and chugging. I'm taking good guesses as far as what numbers might be working, what it might help me with. Now, right away, if I cube -125, I'm going to get a big number. And if I divide that, or if I subtract -27 to it, bless you, I'm going to get a big number. Bless you. And then if I divide that by another negative number, it becomes positive. You okay with that? So it's a positive big number, not on my graph. So that means that somewhere that this had to turn and go back up. But it probably did it a lot more radically because it does this right away. So there's probably this hook here, and it probably does the same thing. It hooks here. That's probably what that graph looks like as a rough sketch. Now, if I want to check it, all I have to do is just throw my calculator. What was it? X cubed something? Over 2x? Okay, so it tailed off a lot slower. All right. Now, if you change your window, just so you get the idea. So it's bound real quick and it's binding real fast the other way. There's a very steep, I'll worry about that later.
How did that, where's the other one?
What other one? Remember, I made the boundaries so wide, if I narrowed this in, it's drawing down towards the asymptote. It's just getting so close to the 0 line. Same thing with this one's curving up to the 0. You just don't see it because it's pinched in. So if I keep it at the y values real tall, I change my window to the x values, making it narrow. If I make my x min at like -5, my maximum at 5, you'll probably see it. See how it's coming in and just whoosh. That's what it's doing. Okay. Sound effects at no extra charge.
So it's just like when you zoom in, it's like a wider.
Yeah. The other questions that you wind up with that are in here, since these were just the ones that you were just identifying graphs and stuff like that, identifying the parts, they're not going to be as clean as the ones that you'll come across that say graph. Because when you get to the ones that say graph, it's going to be easier. They are made so that you can find values that make a little bit more sense. What I was trying to show you with some of these values here, guys, is that when you get into this, you can easily start to pick and choose where you should go. Just trying to get you, I want to say more familiar, more apt to try to plug and chug and pick values, okay? There's an example in here that we haven't looked at yet. I can't remember what it was. This one. I want to do the whole gamut of this problem to show you how you can pick. Bless you. So let's add this one to our notes, and then we'll just add stuff to the homework and stuff tonight, okay? Oops. Let's go through the whole process of y equals 3x squared over x squared minus 4. Because this problem here winds up probably being, I don't want to say worst case scenario, but what happens is that you wind up with a lot of information you can use. So if we start this one out, we have y equals 3x squared over x squared minus 4. The very first thing we're always going to check for is our x-intercepts. We find our x-intercepts by locating the zeros of the numerator. You got a 50-50 chance. So our x-intercepts will be at 3x squared equals 0. So my x-intercept is going to be at x equals 0. Are we okay with that? My vertical asymptotes is going to be at the zeros of the denominator. So it's going to be at x equals plus or minus 2. And this goes with the question you were asking earlier. When you can factor it through, you move and you get the square root plus minus. Yes, sir?
Isn't the x-intercepts at the zeros of the denominator?
Nope, those are vertical asymptotes. And then lastly, your horizontal asymptote. Since m equals n, it's going to be at y equals 3. Because you use coefficients, 3 over 1. Okay? So, we get out our graph paper, and we plot. All right, vertical asymptotes, plus and minus 2. Horizontal at 3. X-intercept at 0. Now this, when you look at it, this breaks your graph into 6 different possible areas. Okay? You've got a region below 3 for y to the left of -2, in between 2 and -2, below 3 or above 3, and same thing over here. So what you're going to want to check then is that you want to check values in the domain in here, and in here, because you have different places that you can find stuff. So what I'm going to look for, going from left to right, I'm probably going to pick -3, -4. That'll get me the stuff on the left. The stuff in the middle, I'm going to do -1 and 1. And the stuff on the right, I'll do, again, 3 and 4. Are we okay with that? I'm just, it's sectioned off into basically 3 different domain restriction areas. So the graph could have 3 different parts to it. By knowing where the graph is going within those values, I can plot it, okay? So I just plug and chug. What's -3 squared? 9 times 3?
47.
47 is in my numerator. The denominator will be 9 minus 4, which is 5. So this is a little more than 5, 5 2/5. Okay? So at -3, I'm up here at 5 and change. You do the same thing at -4. Real quick. Will -3 and +3 give me the same answers?
No. Yes.
Yeah. In this case, they will, because it's just x squared. So basically, I just killed 2 birds with 1 stone. Do the same thing with -4. I get 16. 16 times 3 is
40.
42.
8.
48. Oh, yeah. And then 16 minus 4 is 12. I have 4. So it's moving downward, which means it's moving downward here. So now you can see on your tail ends, there's a little bit of an arc. And a 1 and a 2, and a 1 and a 2. Bam, reference. So you probably can go ahead and say, hey, it's doing this. Now I check it at 1 and -1. Well, I get 3 over -3, which is -1. That's convenient. That one. That's a pretty graph. Not a pretty giraffe or a giraffe, but it's just a pretty graph. Sorry. It made you feel bad for me for a minute there. You were like, I don't know if I should laugh. So, interesting, isn't it?
So what does that mean?
You get a really funky looking graph. Sometimes when you wind up with, basically what happens, like a problem like this, is when you have a quadratic in a denominator that's factorable, you'll have double those, and then if you do get another asymptote thrown in there, you can easily break it into 3 different places that things happen. That's just how it works. Okay, what were you gonna ask?
I was gonna say, can we throw it in the calculator and see
Sure. Yeah, throw in the calculator. What was it? It was 3x squared.
I was just doing that.
exciting, isn't it? What's that?
I said you're so pleased.
Thanks. It's like we did something right. Oh, it looks really weird because our window's all messed up. If I put it at a 5x5, it'll look nicer. Oh, should probably go back 10. Oh well. Mm-hmm. Oh, just wait till we, I mean, this is one of the funkiest graphs we've done so far. Wait till we graph some trig inverse functions, then it gets really awesome. It's great. Let's do another one. It's good fun. There's a hole in the bucket. Here lies a hole. What?
I get to go to help make a collage.
One that has a hole in it.
Oh, you're making a collage?
I don't think it does. I'm trying to remember two.
Like, it's gonna be weird because, like,
I'll play it in a minute, no worries.
you know, all
I'm
this
trying to remember. I'm trying to think if 30 had the hole in it or not. Let's look at 30 real quick. I told you I'll play it later, don't worry. Rush is a band that's been around for over 40 years. They're having their 40th year anniversary this year. It's just 3 guys, and they're what you call a very, very technically proficient band. What that means is that the drummer, Neil Peart, is probably the greatest drummer of all time. He has a doctorate in percussion, and what he's able to do with the different beats and stuff like that. They change tempo, change beats, and the time signatures they use are just stupid. Just randomness, and then they change it back and forth, and it's a very technical band as far as how the music is created, not like grab some chords and just rock, but they make it sound like it. So it's pretty cool how they do things. Anyway, so back to this stuff. Again, you'll see how you've got an m equals n, so you're going to have the horizontal asymptote at 2. We know that right away because the powers are the same. But let's find our zeros for the numerator. 2x squared plus 3x plus 1. So what times what's 2 you add together to get 3? 2 and 1. Convenient. So 2x squared plus 2x plus 1x plus 1. Factor it out. We have an x plus 1. And then we have plus 1. We have an x plus 1. Anyway, perfect. We have zeros at -1 and -1/2. Those are our x-intercepts. Vertical asymptotes. Again, factor it, x squared minus 5x plus 4. We get x minus 1, x minus 4. So asymptotes at 1 and 4. The horizontal asymptote's easy. 2. You okay with that? So let's look at it. We have enough information to plot. We have -1/2, -1, 1, 4, and 2. So again, we've got this range, or this domain area within here and here. And I still need to figure out what's going on around here. Okay. It's just a matter of plugging and chugging. I just wanted to show you that some of these things can get a little fuzzy if we're not careful because there's a lot of stuff to it. Okay. Let's just do this. We're not going to deal with a quiz tomorrow. There's no way. I want to still do science. We didn't have a chance to do those. Yeah, we're going to. Just sort of some random things. We might wait until. This unit doesn't take all that long, and generally speaking, the graphing portion of it really is pretty simple. Usually, we don't get too crazy as far as having to plot out, you know, like some of the ones we were looking at yesterday where you had those cubic functions, you had to do so much work to find all those different zeros and all that. Normally, since I'm not letting you use the calculator to get through that, a lot of times you don't have to worry about that on a quiz or a test. A lot of times it is, can you identify all of the parts? Just kind of like that. Can I identify where my x-intercepts are, my y, my horizontal asymptote, my vertical asymptote? If I did have the case where there was a slant asymptote, could you find it? That kind of thing. We're running, I mean, I know we still have like 10 minutes or whatnot, but we just don't have enough time to really talk as much as I'd like to about that slant asymptote. So what I'm thinking of doing then is I'll give you guys some graph problems tonight of this stuff, where you still list through everything. Tomorrow, I'm going to add in some slant asymptote stuff from the pre-calc book, and just make a copy of a couple problems, just type something up for you guys. And then come Monday, what we'll do is bum rush, multiply, divide polynomials, which is basically factoring, cancel things out, is really all it is. And then maybe what we'll do is just not quiz on this and just kind of put it all together. Remember I said we just take 2 quizzes usually in this section? We'll just take 1 test, because generally speaking, once we get past graphing, all that's left really is solving equations. Okay, and it's really not that terrible. But we can we'll play it by ear, see how we come through after slant asymptote stuff tomorrow. Because I can't crush all that in a day. It's just not right. It's just not fair. Does that seem okay? Because yesterday was awful. Terrible. So, anyway, let's do this. Same section, next page over. Why don't we do?
So what we would need to like do all those different things.
Yeah, what I would do is, see how on the left-hand side you've already got the 1 and the half?
Yeah.
Or, sorry, the negative half, negative 1. I probably want to check it at -3, you know, and at 0. Because I can check 0 real quick. I get a 4th, so I kind of get the idea of where things are going, or where it's coming from. And then I would check it at, 2 and 3. Then I check it again at 5, 6, and just pop points like that. Well, let's do this. Why don't you guys start 30 as the first problem then? We'll do 30. How many graphs you got left on your sheets from yesterday? You didn't have to graph anything though, you just started to, right? Those 6?
Yeah.
So how do you have left? Like
3.
3 left? All right, let's do 30. 31. And let's see.
Are you gonna start with the 10s?
Half an hour break.
36. No, let's just graph these 3 because it was good to get the idea to start to plot through so you get the idea of where the domains are going to go. But we will revisit that tomorrow sometime extra.
Which one?
30. So you finished 30, 31, and 36. You guys all had three spots left on your graphic, right? Okay. We'll do that and go from there. And then we'll do slant asymptotes tomorrow. So just not enough time to do it. But it all boils down to synthetic.
These days when my hands are freezing, I'm just gonna come up and put on the right there. That was fun to see how you guys did it.
Thought we'd have time. No time. There's those two, right? Yeah.